Hello. Hello, everyone. I can't see your face yet. Can you please turn on your webcam? Great. How was your Chuseok, the Korean Thanksgiving? Hope all of you have enjoyed your holidays. Sorry about 2 homeworks, which was due today and the Wednesday, but I still hope you have enjoyed the holidays with your family or friends or just taking rest. I don't know. So yeah, most students already have submitted their project proposal, which was just due now. So thanks for all of your work, and myself and my TAs will do our best to grade them as soon as possible, and we're going to select about 20 projects based on the criteria we have mentioned before. So yeah, please keep tuned, and great job for all of the work. So today we are going to finish a few more slides in the lecture 5 in convolutional neural networks, and we will continue to training neural networks, the practical issues. Before we move on, as usual, we are going to review. So it's been a long time, about a week ago, so probably many of you already forgot a lot of what we have learned. So let's check. Okay, today I'm going to ask to Eugene Kim from Mechanical Engineering.
Yes.
Okay, yeah, so I'm going to give you some very specific questions. So please answer. So suppose we have an input vector of dimension 20, and our output will be 10-dimensional vector. Then what is the size of the upstream gradients? So input is a vector of 20 floating point numbers, and output is a vector of 10 floating point numbers. What would be the size of upstream gradients?
Oh, 10 by 20.
Why?
Because the gradient between vector and vector is the
I asked upstream gradients. What is upstream gradient?
Upstream gradient is
What was the upstream gradients?
Upstream gradient is the prior gradient.
Yes, it was the gradients coming from the following nodes, right?
Yes.
So what should be the size of that?
It's the same with
yes, just be more confident. I think you know the answer.
Following element size.
Okay, okay, thank you. Let me ask another students. 김자유?
Yes, Professor.
Yes. What's the answer for this? We have an input of dimension 20 and output of dimension 10. What should be the size of the upstream gradients?
10?
10. Why? It's correct. Why? Okay, so yeah, we mentioned that all the time, the forward pass and the backward pass, we have always the same number of dimensions in each edge. So given the node, we have the input and output, and the upstream gradients coming from the output side. So the dimensionality of that should be always same as the dimensionality of the output. Because we have output of 10-dimensional vector, its gradient should be also in the same shape. It was a simple question. But let me continue to another mechanical engineering major students. Kim Ji-ho?
Yes, Professor.
Yes. Now, what is the dimensionality of the local gradients for this problem?
So what was the size of the matrix?
So the input was 20-dimensional vector. Output was 10-dimensional vector for this node.
10 times 20.
Okay, why is that?
So we have to calculate the matrix. So for the vector, so we have to multiply with two vectors. So it should be the reverse size.
Yes. Yeah.
Yeah.
Yeah. So yeah, as he said, this was a vector-to-vector case. So we have to have the all pairwise relationship needs to be computed as the gradients. So we have the matrix of size 10 times 20 in the local gradients. So okay, good job. The last question, 백서하. It's not here. Okay, 이아영. 이아영. Okay. 전명근.
Yes, Professor.
Yeah. So now we have the size of the upstream gradient and local gradients. So I'm going to ask the last one, which is the downstream gradients. So what is the dimensionality of that?
It's same with the coming elements dimension.
So okay. So yeah, I set it as 20. So yeah, it should be the 20.
Yes.
Yes. Okay, that's great. Why?
Because coming dimension is it's just the output of the previous node, so we should have the same dimension.
Yeah. So yeah, he said we should have the same dimensionality of the input, the dimensionality of the input and the downstream gradients here. Or you can also answer that we have the dimensionality multiplied with upstream gradients and local gradients. So that's the same, which is 20 dimensional vector here. So I asked a really simple question to everyone, but I think most of you are already forgot because we had very long holidays last week. So please review the materials. This is really important. And otherwise, yeah, you're not going to follow the next materials we are going to cover. So, okay, let's ask the next question to data science students. 경선?
Yes, Professor.
Okay, so in the last lecture, we learned about convolutional layers, and we talked about 4 main elements when we define a convolutional layer. So what were those 4?
I don't understand the question as well. Can you explain more specific?
Okay, so when we define a convolutional layer, we have 4 essential parameters, hyperparameters we have to decide.
Yes.
What was that?
Filter size?
Yes.
Stride and padding size?
Stride and padding, yes. What's the last one? We need the number of filters, right?
Yes. Number of filters.
Yeah, we need to specify these 4 to have a convolutional layer in our neural networks. So how many filters we have, and what's the size of those filters, and what's the stride size and the padding size. So these 4 needs to be defined. Thanks, Hyung-sun. And we mentioned that the convolutional layer is much more efficient than the fully connected layers, which means we have much less number of hyperparameters. So how that was possible, under what assumptions? We talked about 2 main assumptions. So what was that? Let me ask this to Yurim, 최유림. She's not here today. Okay. 조동규.
Yes, Professor.
Yeah. Do you remember the question?
Yeah. You told us that there are 2 advantages, strong points of the convolutional networks. And that would be that the filters, which are the parameters, can be shared upon different layers. That's one.
Upon different layers? What do you mean by that?
So, I think I'm confused with the question. May I?
So we learned that convolutional layer has much less number of parameters to learn. So that is because of our assumptions, actually 2 assumptions. So what was that? It's okay. Let me ask the same question to Kim Do-gyun.
Yes, Professor.
Yeah.
I'm not sure about your question, but the convolution network has like dimension reduction.
Dimension reduction. I think you are confused with 1-by-1 convolution. That is for the dimension reduction. So what is the main assumption of the convolution layer? That's my question.
Convolution layer. Assumption. The spatial locality.
Yeah.
So.
Do you remember the other one? Yeah.
Positional invariance.
Yes, that's positional invariance. Yeah, location invariance. Yeah, that's the same thing. So yeah, thanks. Yeah, as he said, the main assumption of the convolutional layer is that the output is affected only by the nearby pixels, which is summarized as spatial locality. So we don't have to refer to the pixels far away or the features far away from the target pixel. That's one. And also, and another one is we use the same filter in all the places. We apply the same one. So that's the location invariance. So for example, when we would like to recognize some human face, we actually use the same filter in all over the place to locate where the face is. So because of these two things, we can significantly reduce the number of the number of parameters to learn in our model, and that was really dramatic. We have computed some example in the last lecture, comparing the fully connected and convolution layers. So please review the material if you are not following. And I also uploaded the reading materials, which is covering some more details about what we are covering in the lecture. Otherwise, the content will be getting more difficult and difficult. So please keep in mind that what we are doing now is kind of review, and you have to actually you have to be able to answer all of these questions right away. Please study. Okay, so let's move on to a pooling layer, which is the last part of this convolutional layer. So in the last lecture, we have learned about convolutional layers, and pooling layer is usually used together with the convolution layers. So what is a pooling layer? With downsampling, we would like to make the representation smaller and more manageable. So suppose we have 224 times 224 times 64, the number of filters. Pooling applies some deterministic operation to reduce the size. The main goal of this is actually reducing the size, keeping the essential information. So we call it also as a downsampling. We may take average or max or some other deterministic function to reduce the size. And this has some effect of denoising, because in some pixels may be noisy when we take some pictures using camera. Sometimes some pixels are noisy, and when we do this kind of downsampling, those are smoothed with the neighboring pixels. So we have also some effect of the denoising. So this is really simple. When we have some examples like this, with 2x2 filters and try 2, which means we operate something on this 4 pixels with orange color, and the next one will be try 2, so will be applied to this green and then blue and yellow. So we may apply some max pooling, which takes the largest value among the participants, or we may take the average among those. So something like this. And if we draw this as a example picture like that, suppose we have some diagonal line like this. This is higher resolution. So you see that these are in a better quality of the image. But when you apply the max pooling, which means among these 4 pixels, you take the largest intensity. So that will be something like this. It will be the resolution became half and half for both sides, but all the values are taken from the max. And when you take the average pooling, the shape will be like this. So at the actual diagonal, you have the higher scores, but a little bit off diagonal, the intensity gets smaller because it takes the average with the black and whites. actually, this figure is not as correct as I intended, because usually white means larger values and black means 0. So it's the opposite, but I think you can follow what's the meaning of this. So let's take an example. So suppose we have 4x4 input image, and we apply the filter size 2x2 with stride 1, or stride 2, or feature size 3x3 and stride 1. So with filter size 2x2, the first one will take the average or max over these 4 elements, and it will be written in the first element. And because the stride is 1 with the first example, in the next one we'll be just moving 1 pixel to the right, and we compute the same thing. And again, but if the stride is 2, in the middle one will be skipped, and we have just 2 numbers as output here. And when the stride is 1, we do the same thing in the next row, but that is also skipped in the second example. And the next row will be computed in both in this stride 1 and 2 cases. So we have output size 3x3 in the first example, but 2x2 in the second example. What about this case? We will compute using the 3x3 filter. We will take the max or average here, and that will be written here. And because the stride is 1, it moves to the right by 1 pixel, and we compute the same operation. So it will output the same size of the matrix like that to this case, but the actual number written here will be different. So this is the pooling layer. This is much simpler than convolutional layer, right? So here's the summary. So when you have an input of width times height times number of channels, and pooling layer needs 2 hyperparameters, which is the filter size, or we call spatial extent here, and the stride. So with just 2 things, we can compute the output size using this formula. Important thing here, the number of parameters of pooling layer is 0, because this is deterministic function. We're just taking the average or max. We don't learn anything from the data. Given some input matrix, we just compute using the deterministic functions, and it just outputs. So again, number of parameters with pooling layer is always 0, regardless of these hyperparameters. Okay? Okay, last question is, do we really need a pooling layer? It looks like a special case of the convolutional layers, but it's definitely much weaker because we don't learn anything from the data, right? So do we really need this pooling layer? As I mentioned, the main purpose of the pooling layer is reducing the size of the input image. So we may use the convolutional layers with larger stride to have the same effect, reducing the size of the image. So do you think this claim is correct or not? Actually, this is a ongoing discussion. So it's not confirmed yet, but recent trends actually indicate that this is true. So the pooling layer is less and less being used in modern neural networks, because we can use only the conv layers to have the same effects. And if you are interested in this kind of discussions, please report to this paper. So we are going to see an example of like that using only the conv layers without pooling layers in generative models. They're actually, pooling layer is almost disappeared. Nobody uses pooling layers recently. So this is the end of lecture 5. And before we move on, if you have any questions, please feel free to ask now.
Yeah, I'm sorry. My question would be for the pooling layers. Do you also have? It's basically just that you apply the same operation to every slice of the previous layer, right? It's not that you have different operations for every slice like you would have for the convolution operation, right?
Sorry, I don't understand your question.
So for a convolutional layer, we have to also give the number of filters. when we do pooling, we just apply the same operation to every channel of the previous layer?
Exactly. It will be applied channel-wise, and because we have the deterministic function to apply, we don't need to specify the number of channels here.
Okay, perfect. Thank you.
Any other questions?
Oh, can I ask a question?
Sure.
Oh, so I'm wondering about the difference between max pooling and average pooling as practically. I mean, like, for example, like for this kind of data, max pooling works better, and for this kind of data, average pooling better. So how does this difference pooling work in actual programming?
It's a good question, but there's no answer. Actually, you should try both in most cases. So the underlying principle of the max pooling is, you may remember that we are trying to locate some patterns we would like to find in the image. And if, for example, if we find some face in one of these pixels, we would like to keep that information regardless of where it's actually coming from when we reduce the size. So in that kind of cases, we use max pooling. Otherwise, it will be just averaged with something random, other pixels. So max pooling was designed to such a kind of cases, but in some other cases, we need average pooling. I don't have full list of examples here, but in many cases, actually, either of them or both of them make sense. And one practice is actually you apply both and concatenate them. Usually when you do that, actually the performance gets better slightly. But if you see just negligent improvements, maybe you can just use one of them. So it's really empirical. It's unfortunately, I don't have definite answer for that question. But that's a really good question. Thanks.
Thank you.
Okay, so let's stop recording here.